Okay, so for this video, we will talk about cable subjected to uniform load. Okay, so say for example, you have your pin support, which is supporting a cable subjected to a concentrated load at the midspan. Okay, so you have here your cable, then you have your concentrated load, let's say having a magnitude of P. Okay, so the distance between the pin we don't know. Let's just denote the distance between the pin and the pin support to be distance of L. Okay, and the magnitude of P is also unknown. Okay, next, if we try to add another concentrated load, let's say same magnitude P and then P on this. If this one is L over 2 and then L over 2, then this P here will be subjected to L over 4 and then L over 4. So you have here magnitude P and then magnitude P. Then that would end up with a system which looks something like this. So you have your pin and your pin support. So you have here your load P, and then your load P. So you have here P, P, and P, same span, that one is L. Okay, next, if we add more, let's say you have here, you will try to apply here another load P, another load P, and then another load P, and another load which is P to be applied on this point, that point, and that point. Then that would end, or that would result your that would result to a cable which will form a parabolic geometry. Okay, so if you try to bring this down, okay, since they are of the same magnitude, if you try to bring that down and then try to organize them as a load which is, or which has the same magnitude over a span of L, then you would have your uniform load. Okay, so basically you would have your uniform load in your system. Then you have the cable supporting that load to be parabolic by uh, parabolic in terms of its geometry. Okay, of course, since this one is of the same level, let's just assume that they are of the same elevation. Since that one is of the same elevation, then you can say that that one is a vertex of the parabola. Okay, so you have here your cable system which supports a uniform load. Okay, now in terms of carrying these loads, what would be the response of our cable? Okay, so in this particular subject matter, we still have the assumption that your cables does not resist bending or is flexible, and then another is your weight of the cable is negligible compared to that of the loads. Okay, so how do we calculate, or how do we get the response of this particular system? Okay, so again, since this one is a pin support, then it is, you can say that you would have your horizontal and vertical components for each support. Okay, then you would have also your resultant for that particular support. Okay, now that particular resultant there, okay, would be tangent to this particular point. Okay, to this particular point. Okay, so with that particular argument, if we try to cut a section, let's say on this particular portion, you take that as one free body, then you would have here your system. Okay, so you have your load over here. Okay, and then you have also again your reaction. Let's denote this one as R. You have your horizontal and vertical components. And then as per argument a while back, that R is tangent to this particular point, then you can say also that the tension developed at that particular point, let's say point O, is also tangent. Okay, so let's denote this one as force F. Let's have a color for that one. Okay, so that would be your force F. Okay, so for the magnitude of this one, since you have here your R and then your F as the forces acting, also your load acting, then this would be, you can say that this is on the state of equilibrium. Okay, so since it is on the state of equilibrium, these three forces present in your system would make your body stable. Okay, now let's talk about the lowest point, which is the vertex. Now, since you have here the lowest point by principle of differential calculus, the tangent line at this particular point would be horizontal. Okay, so therefore, if you try to pass a section here, isolating this one, taking it as one free body, then you would have a system wherein you have this one as your system. That would be your free body diagram since you have isolated that one. Now, when you isolate that one, again, just don't forget to reflect the forces which are acting on those cut sections. Okay, so in this particular case, since you have passed a section on that particular lowest point, let's say lowest point there is A, then you would have here a tension which is tangent to that particular point wherein it happens that it is horizontal. Okay, so that would be horizontal. Let's denote this one as T. Okay, and then of course you have your reaction at the pin support. That would be R. Okay, that would be pin and that would be R and T. Now, since you have here your forces, set of forces, you have your T, you have your R, and then you have your uniform load, then you can say that it is on the state of equilibrium since the whole system is on the state of equilibrium. Okay, so if we try to analyze the system, this particular free body diagram, you would have three sets of forces. You have R, T, and you can get the resultant of this uniform load, which is acting at the center of gravity. Okay, now the force acting on the center of gravity would be the equivalent concentrated load of this particular uniform load, where in this case, if this one is L over 2, and then the magnitude of this one is, let's say, W, then your concentrated load, let's denote that one as what, Q. Let's say Q. Okay, let's denote that one as Q. Your equivalent concentrated load Q now is equal to W times L over 2. Okay, so this is not a formula, no? This is just a general conceptualization of the system. Okay, now with that, you have here three forces which is making the body on the state of equilibrium. So therefore, we can also apply several principles like your force polygon. Okay, so you would have here Q would be on a downward direction. Okay, then T would be on the direction which is to the left. Okay, so again, that one is Q, this one is T, and then of course you have your resultant R. Now that should close since it is a force polygon. Okay, so that would be, since this one is vertical, that one is horizontal, you can say that this one is perpendicular. Okay, so simple as that, ano? So that is how you treat this kind of problems. If you try to analyze, you would have here, let's go back to this particular example. Okay, so in this particular example, you have here, if you try to concentrate your or focus on F there would have, F there is inclined of sort. Okay, so that one is inclined with respect to the horizontal. The angle of inclination, we don't know, but you can determine that using calculus. So you have here an angle of inclination of theta. Okay, let's just assume that that one is inclined with an angle of theta with respect to the horizontal. Now, if you were to derive the amount of, the components for this f, since you have an angle of inclination, you would have a horizontal component and a vertical component. Now, surprisingly, f here would have a horizontal component which is equivalent to t. Okay, and then the vertical component would be equal to what? Let's say the vertical component is v, that would be equal to f times the sine of theta. Of course, t there is equal to f times the cosine of theta. But of course, I can assure you that this one is t. So therefore, any point along the cable, okay, if you try to pass a section, you would have a horizontal component of t for each point if their components is to be resolved. Okay, and then as for the lowest point, you do not have any vertical component, then you would have just the horizontal component of t. So we can say that the lowest point is the point wherein the tension is the smallest. Doon yung pinakamahinang tension na na-develop. While the highest tension can be found at the supports. Okay? So, highest tension can be found at the supports. Okay? Whichever is higher in terms of elevation, with respect to a fixed datum, that would be the point wherein you can find the highest tension. Okay? So, we'll have an example for this one for the next video.